What's up? This is Mario, and welcome to Awesome Acoustics. In this episode, we will talk about additive synthesis and spectral analysis, also known as Fourier synthesis and analysis. Spectral analysis is a super useful tool to study any vibration phenomenon. That is, not only sound, but also other types of mechanical vibrations such as car suspensions and earthquakes, electromagnetic waves such as light and radio waves, alternating current, and even quantum mechanics. So, the tools that we're going to learn today are actually useful in all of these fields. The sine wave plays a fundamental role in additive synthesis and spectral analysis. If you want to understand the sine wave in detail and how it originates from trigonometry, I made a separate video explaining it, but for this video, I will give a summarized version. The trigonometric function sine is a function to which you give an angle and it gives you the length of the opposite leg relative to the hypotenuse. For example, the sine of 30 degrees is 0.5. If the hypotenuse equals 1, then the sine function gives you the length of the opposite leg directly. If we plot the sine function with angles from 0 degrees to 360 degrees, we get this curve, which we know as a sine wave. In fact, it is called a sine wave or sinusoid precisely because it comes from the trigonometric function sine. The reason why we can calculate the sine of angles greater than 90 degrees is because in those cases the right triangle flips. And if we calculate the sine of angles greater than 360 degrees, the pattern simply repeats. A gradual increase in angle is basically a circular rotation. And we can consider the sine wave as a single dimension of the circular rotation. The phase of a wave is the specific moment of the circular rotation the wave is at, between 0 degrees and 360 degrees. For example, when the phase of a sine wave is 90 degrees, its value is 1. Now, how do we add two waves? There are formulas to sum certain combinations of continuous waves, but an easy way to understand it is by discretizing the waves and adding each pair of points. In the end, we will mainly be adding digital waves anyway, which are already discretized. I'll show an example with these two waves. Here, I'm going to discretize the waves every 30 degrees and sum each pair of points. In this specific example, each pair of points has the same value. Therefore, the sums would be double the amount. So the resulting wave, in general, would have twice the amplitude. For this example, I discretized with few points, but in practice, I would recommend a much finer resolution. When summing two waves with different amplitudes, different frequencies, or different waveforms, the result is more arbitrary. Before we start with spectral analysis, personally, I think it helps a lot to understand it if we first look at additive synthesis, also known as Fourier synthesis. This is a process in which we build different waveforms by adding only sine waves. And within this, there are the Fourier series, which are basically recipes for building certain waveforms through additive synthesis. For example, this is the Fourier series for a square wave. This may seem overwhelming, but this formula can be interpreted as a series of simple steps. The first step is to decide what amplitude and frequency we want for the square wave, say A and F. So we start with the first component, which is going to have an amplitude A times 4 over pi and frequency F. Then we add the second component, which is going to have an amplitude A times 4 over pi divided by 3 and frequency 3F. Since we are adding a small trough to a large crest, the result will have a small cavity in its crest. The third component is going to have an amplitude A times 4 over pi divided by 5 and frequency 5F. The subsequent components follow this pattern by going through the odd numbers, that is, 7, 9, 11, 13, etc. The pattern is infinite, so we have to stop at some point. This can be when we start to generate components that are outside of our audible range, or that are higher than the Nyquist frequency, or that exceed the capabilities of the loudspeaker. This would be the sequence of waves that results from adding components for a 400 Hz square wave. Each component is a sine wave, so the wave with only one component is a sine wave itself. Here we can see how it gradually begins to take the shape of a square wave. Now let's listen to how the timbre also starts out as a sine wave and gradually approaches a square wave. We can also approximate the sound of a real instrument with additive synthesis. In this case, it will be a melodica playing the note C5. Using a tool in Audacity that I will explain later, I can find the amplitudes and frequencies of the components. Then, I generate sine waves with these numbers. Let's listen to the result of gradually adding components. I will also fade in and fade out to mimic the instrument. In this case, the result is quite good because the melodica has a very consistent sound. But in some other instruments, such as piano, guitar, or violin, the components have a more complex behavior and their amplitudes vary with time. So, additive synthesis is not the best option to synthesize these instruments. At the end of the video, I will show some examples of additive synthesis using a synthesizer. But first, we need to know how to read frequency spectra. Now, we can start talking about spectral analysis. Spectral analysis, also known as Fourier analysis, consists of describing any waveform as a sum of sine waves with different frequencies and different amplitudes. Basically, it is the reverse procedure to additive synthesis. But why use sine waves and not any other type of wave like the square wave? Well, it turns out that the sine wave is quite special. When we put a waveform into any acoustic, electrical, or mechanical system that behaves like a filter, this system will change the shape of the wave, except for the sine wave. Its amplitude can change, but it always keeps its sinusoidal shape. This is why the sine wave is also known as a pure tone. This allows us to use the sine wave to accurately study how these systems react to different frequencies. The sine waves we obtain through spectral analysis of a wave are called its frequency components, although in common conversation they are simply referred to as frequencies. Mathematically, these components are obtained through a formula called the Fourier transform. This graph is called a frequency spectrum. Here we have frequency on the horizontal axis and amplitude on the vertical axis, and each line represents a sine wave. That is, the horizontal position of each line gives us the frequency of the sine wave, and the height of the line is the amplitude at that frequency. When we have time on the horizontal axis, we say that we are in the time domain, and we see the waveform. When we have frequency on the horizontal axis, we say that we are in the frequency domain, and we see a spectrum. If we apply the Fourier transform to a sine wave, its frequency spectrum will only show one component. This is because to form a sine wave, we need, well, a single sine wave. The frequency and amplitude that we see in the frequency domain are the same as those that we see in the time domain. Now, let's apply the Fourier transform on a square wave. What we are going to see in its frequency spectrum are the same frequencies and amplitudes of its Fourier series. In the previous episode, I mentioned how different waveforms could have different loudness even with the same amplitude. This is because the loudness that we perceive is not exactly related to the amplitude of the waveform. but rather to the sum of amplitudes of all its spectral components. So, a square wave is louder than a sine wave with the same amplitude because it has more energy added from all its components. The spectrum of a square wave is a known analytical solution. But for other waves, we would have to do this calculation manually, which would be ridiculously laborious. Fortunately, today we have the support of computers. There is a digital version of the Fourier transform called the fast Fourier transform, which is optimized to be computed by a digital system in a fraction of a second. Any software that calculates the frequency spectrum will be using this algorithm. As we mentioned in episode 4, one downside of the digital world is that the resolution isn't perfect. So, when we get a spectrum of frequencies with the fast Fourier transform, what we get are not perfect lines, but peaks. However, it still gives us much more information than we could get manually. It should be noted that so far, I have shown amplitudes on a linear scale. But software will typically display component amplitudes in decibels full scale, which is a logarithmic scale. That's why the ratio between the components looks a little different in one spectrum versus the other. If you have not watched episode 2, there I explain the decibels in detail. When we obtain the frequency spectrum of a musical tone produced by an instrument, we see various frequency components. The lowest is called the fundamental frequency. This frequency determines the musical note of the tone, which are the frequencies I explained in the episode on musical frequencies. The fundamental frequency and all frequencies that are multiples of the fundamental are called harmonics, and the fundamental is considered the first harmonic. The rest would be the upper harmonics or overtones. Typically, musical tones will only have harmonic components, that is, components with frequencies that are multiples of the fundamental. For example, if we play the note A3, which has a frequency of 220 Hz, then the tone will have components at 220, 440, 660, 880, etc. The square wave is a somewhat special case, since it skips the even multiples. Strangely, bells and some other tonal percussions produce inharmonic components, that is, frequencies that are not multiples of the fundamental. This is due to the shape of such instruments and the dispersion of bending waves, but that is a more advanced topic that I will not go over in this video. The sounds where we do not distinguish a specific musical note, such as those of non-tonal percussions, will not really have a fundamental and components at specific frequencies, but rather they will have a complex spectrum. Here, we can see that each musical instrument has its characteristic spectrum even when they play the same note. The frequencies are the same, but their amplitudes are different. So, the amplitudes of the components is what gives each instrument its timbre, or more accurately, the ratios between the amplitudes. We can also see that the fundamental frequency is not necessarily the one with the greatest amplitude. Musicians often refer to timbre as the color of the tone. This is an analogy of how the colors that we perceive visually are also combinations of different frequencies, just that in the case of colors, they are electromagnetic frequencies. The waveform, the frequency spectrum, and the perception of timbre are all directly related. However, in the first episode, I mentioned that timbre is actually more related to the frequency spectrum than to the waveform. This is because while the phase of the components affects the waveform, it does not affect our perception of timbre. Let's look at this example with a square wave. If we add all the components in phase, that is, that at some point they all coincide in phase, we effectively achieve the square shape. If I randomly shift the components so they're not in phase, and add them together, then we get this wave, which looks very different from a square wave. But what happens if we listen to them? This means that what we are hearing is not so much the waveform, but the components that make it up, regardless of their phases. Loudspeakers have certain frequency ranges that they can reproduce. Even if the frequency of the wave itself is within the range, we have to remember that the wave can also include higher frequency components. If we have a mid-range loudspeaker with a range of 200 Hz to 2 kHz, and we try to play a 500 Hz square wave, the components higher than 2 kHz would be removed, which would change the appearance and the expected timbre of the square wave. The second wave is what would actually come out of the loudspeaker. Technically, this is filtering, but we will talk more about filters in the next episode. Even if we think of waves as sums of only sine waves, this does not mean that in real life all sounds have to be built by adding only sine waves. For example, to generate an electrical square wave, it is not necessary to add a practically infinite number of sine wave generators with different frequencies. We can simply have a switch that toggles between positive and negative voltage, and with that, we successfully generate a square wave. Even if a wave contains many frequencies, a loudspeaker cone will follow only one movement, which is the shape of the waveform, so long as all of the wave's components are within the loudspeaker's range. But if we go back to the example of the square wave and the loudspeaker, it is much easier to understand and predict the change in the wave by knowing the spectrum of the wave and the frequency range of the loudspeaker. So, spectral analysis is more of an alternative and more precise way of studying waves, the effect of filters, our perception, etc. With our new knowledge of components and spectra, we can explain clipping from another perspective. When the peaks of a sine wave are clipped, more components are now needed to get to this shape. In other words, clipping introduces new frequency components. Generally, when new components are generated by deformations in the waveform, it is called distortion. This is often unwanted, although it is used deliberately for the sound of the electric guitar. If you want to process a spectrum yourself, this is possible in Audacity. First, you select the audio portion to analyze, and then you go to Analyze, Plot Spectrum. This is how I got the components of the melodica in the additive synthesis example. Now, there are some important things to keep in mind about the Fourier transform. When you process a frequency spectrum, you typically select a small portion of the signal, much less than a second. This is because, in a music or speech audio, the frequencies and amplitudes vary greatly in the span of a single second. Whereas the Fourier transform expects you to give it something repetitive. So, the spectrum of an audio of 1 second or more does not typically give us useful information, unless it is a constant sound. Then, when you select your audio and process it, what the Fourier transform is going to see is a signal where your selection loops infinitely. With this selection, what the Fourier transform sees is an infinitely long sine wave, so there's no problem. The spectrum that it yields is a single peak as expected. However, if I select a portion of audio so that the sine wave cuts off here, then the Fourier transform sees this selection repeated infinitely, with these discontinuities. So, the Fourier transform will be processing a waveform that sounds like this. Although the waveform looks almost identical to a sine wave, the timbre is quite different. For this wave, this is the spectrum that the Fourier transform gives us. As with the timbre, it is quite different from what we would expect for a sine wave, because now we need all of these sine waves to achieve this waveform. When you have a complex signal with many components, it is virtually impossible for the selection to match all periods perfectly. So, to mitigate this problem, the software applies something called a window function. I will explain this in more detail in a video on the mathematics of the Fourier transform. But again, these window functions only help to mitigate the problem. That is, they don't get rid of it. So, when making short selections or when analyzing repetitive waveforms, you should make your selection carefully. Now, all that we've talked about regarding spectral analysis is only for a small portion of audio. So, how do we analyze music or voice where the components vary over time? For that, it would require to take the Fourier transform many times in the span of a single second, and there are two ways to present it. The first way is to display the spectrum as an animation. Each individual image in the animation is a spectrum taken at a certain time. In music software that supports VST plugins, you can download the free plugin Voxengo Span. The second way is with a spectrogram, which we looked at in the previous episode. Remember that here we have time on the horizontal axis, frequency on the vertical axis, and the amplitudes represented with colors. So, a spectrogram goes from left to right just like a wave, but it shows you the components separately. In musical tones, we will generally see many parallel lines, which in this case are the harmonics. As we mentioned in the previous episode, in Audacity, you can activate the spectrogram view in the track menu. You can also activate the multi-view, which is super useful. As I mentioned earlier, I will now show examples of additive synthesis on a synthesizer. First, we will synthesize an organ. I'm going to use 6 sine waves, with these frequencies relative to the fundamental. These controls are for the level of each individual component. And in this screen, you will see the spectrum, which will be continuously updating. And now we will make a xylophone. These will be the frequencies of my sine waves, and they will also have a decay, that is, a gradual drop of amplitude. With that, we conclude this episode. See you in the next video.